So we are starting Unit 10, which is sequences and series, and this is the last unit before the AP exam. Can you believe it? It's gone pretty quickly. Today we're going to start with sequences, and it will feel like a lot of examples and a lot of notes, but it needs to be. This is a topic that traditionally would be covered in a pre-calculus course. I think you may have been introduced to it, maybe a little bit in Algebra 2, maybe in pre-calculus, but you don't have a background, a large background with sequences and series. Actually, geometry talked about sequences a little bit. So we kind of have to get a really good understanding before we go to do other pieces with it. Is this a section or is this a unit that is related to the other units? No, it is not. It's going to feel completely out of left field. We will talk about a little bit of a derivative and a little bit of an integral, but honestly, this is very, very different than anything that we've done in this course until this point. It does not have any basis on Unit 9. This is just a whole new ballgame. So let's start. Sequences. What is an alternate way to represent functions? And we're going to say a sequence. You can use, instead of that function itself, you can use terms of the function evaluated at specific values all the way through. And I know that doesn't mean much right now, but just keep in mind that we're looking at a different way to represent, and not so much your polynomials, but things like e to the x, your trig functions, natural log of x. We can start to approximate those things with other values. So a sequence is a function whose domain is the set of positive integers and whose range is a subset of the real numbers. So right here, integers. Our input for all of these will be integers and we'll count by ones a lot of times. In the introduction, we don't have to count by one, but eventually we'll always be counting by ones. So you're putting in an integer. So a couple of these, we have the graph of a function is this version on the left where we have the smooth curve, that's what we're used to. And then on the right is the graph of the sequence. So the sequence again has the positive integers. So n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So we're not connecting the dots anymore because we're not looking at the decimal values in between. The first graph has an infinite number of points all the way through here. The second graph does not, in between 1 and 5. Now, it would continue forever and ever and ever, but we're just looking at the points. So examples of a sequence, and these are the type that you would have seen earlier in your math careers. We have an ordered list of elements. You can have repetition. So I know in domain and range, you have to look out for repetition. Repetition's okay. It can be finite or infinite. So those 3 dots mean it continues forever and ever and ever. It often follows a pattern. We'll be looking at things that do follow a pattern. And one of the ones that's up there is the Fibonacci sequence. I'm sure you've heard of it, but it shows up a lot in science and nature. And the way the Fibonacci sequence works is you start with 0 and 1, and then you add the previous 2 terms to get the next term. So 0 plus 1 is equal to 1. And then 1 plus 1 is equal to 2. And then 1 plus 2 is equal to 3. And then 2 plus 3 is equal to 5, and so on and so on. So that one's kind of a neat one. So you want to find the next 3 terms in each sequence. So you don't really need me for that. I tried to pick ones that were fairly straightforward. So pause the video here, see if you can come up with the terms in the sequence, and then we will check our notes together. So you can see these are the patterns that I found for these 6 sequences. We have adding 7 in number 1. We have adding 6 in number 2. Number 3 is a little weird. We just added a value to the denominator each time. Number 4 is really 1 over 3 to some exponent, and that goes up by 1 each time. I didn't bother writing out 3 to the 5th and 3 to the 6th. Number 5, I just multiplied by -2 for each of those terms. And number 6, we added 10. So especially like that number 2 and number 6, you might see in an elementary math class or middle school math, but our sequences will get a bit more sophisticated, of course. All right, so now we're on to what does this look like? So probably the strangest thing about everything in Unit 10 is that the notation is different. We're bringing back those brackets. We'll have a lot of n's. We will talk about infinity a lot, and we will eventually get to that sigma notation. That's going to be in our next lesson. So in words here, my first bullet point. If I have a series that goes from 1 to infinity, And we're going to say that, okay, in this particular case, 1 over n is that series or is that sequence. And then S sub n equals 1 over n. That defines the sequence. S sub n is equal to 1 over the n is the nth term of the sequence. I know that's a mouthful. So say n equals 20. I'm just making that up. That means that the 20th term would be 1 over 20. And this is where you want to be careful of recursive sequences, like that Fibonacci one, where every term relies on the term before. Those can be a little bit complicated to write those formulas for, but the ones that are just dependent on whatever position you are in that sequence, those are a little bit easier. So for example 1, we'll write the first 3 terms in each sequence. Very straightforward. We're going to start with n equals 1, put it into the expression, n equals 2, and n equals 3. So if I have a 1, I've got 1 over 3 times 1. This is 1 over 1. I have 1 over 4, and I have 1 over 7. I'm not adding them. I'm not multiplying. I'm just listing them out. That's all I have to do for the first example is just list them out. Just making sure I didn't make a mistake. Okay, good. Now, the second one, letter B, same thing. N equals 1, n equals 2, n equals 3. For most of the things that we'll do, we'll start with 1. They're counting values, 1, 2, 3, 4, 5. Sometimes 0 sneaks in there, but most of the time it's 1. So for this particular problem, I will have a 1 over 1. And then I will have 3 over 8. And then I have 5 over 27. Let me just double check. Okay, so we're good with those. Example 2, same thing. We're getting into slightly different notation. Write the first 5 terms of each sequence. So let's do n equals 1. Do you have to write out the n's each time? No. I am though, because this is a video and we're still kind of new to this. So to me, it helps me to see them. So the first one I know is -1 to the n's. This would be -1 and 1/2 to the first power. And then -1 squared is a +1. And then this is 1/2 squared. And then this is a -1, 1/2 cubed. And this is a +1. Oops, this should be 1/2. 1/2 to the 4th. And then we have a -1, 1/2 to the 5th. So if you notice, but the exponent on the 1/2 keeps increasing, that's fine. But then the sign in the front alternates. It's +1, -1, +1, -1, +1, -1. That is an alternating sequence. So your signs change between positive and negative. And usually we'll attach a 1 right to the sign so that there's always something there, a +1 or -1. Good. Example 3. Find the nth term of each of the following sequences. Assume the indicated pattern continues. So I don't want to write out the next 3 terms like we did in that first example, but I want to be able to say, okay, what is the actual pattern? So sometimes for me, it helps because that first term can be a little deceiving. I like to label them. Here's 1, here's 2, here's 3. And when I look at that, okay, I can see that this is going to be e to the n over n. No big deal, no problem on that one. So let's go to the next one. I have a 1 first term, second term, third term, fourth term. I'm looking at this one a little bit differently. I'm going to say, it looks like the bottom is, I've got this 1 over 3 thing happening. And there's definitely an exponent there. My problem is it's not n exactly, but it looks like n minus 1 to me. For example, if I look at the 1/9, right, that's 3 squared on the bottom, but it's the third term. So if I take 1 off that n value, that n term, then I think I wind up with the correct one. These take practice, and some of you are going to look right at these and be like, oh, cool, I get it, I see it. Some of us, myself included, have to stop and look at them a little bit longer. I'm looking at letter C. 1, 2, 3, 4, 5. I think this one's pretty straightforward. This would be n squared. Whatever n is becomes my exponent. Whoops. When I'm looking at letter D, the bottom to me looks like an n plus 1. It's going up by 1 each time. And the top one looks like a 2 times n. So 2 times 1, 2 times 2, 2 times 3. Yeah, that's what I'm going to go with. 2 times n rather, not 2 times 2. The next one, that alternating piece, what I didn't tell you is how to get that alternating in there. That happens with a -1 in your exponent. So this is -1. I want this to be, I'll show you what to do here in a second. So there's 1 on the top, and the denominator is the actual n term. If we do this 1, 2, 3, 4, 5, that takes care of the denominator. Now, I want the numerator to change signs, but it has to start with a positive. So I don't want this exponent to be n. So I can offset it by 1 and do like an n plus 1. There's a couple different ways to do that. But if I make the exponent n plus 1, then my first exponent would actually be 2, and -1 squared is a positive 1. Yeah, so I like that. Oh, this one's interesting. 1, 2, 3, 6. Well, that thought I have to come back to this one. I did cheat. I thought they were looking for something more interesting, but it is this. They broke it apart into 2 pieces, and they said it's 1 if n is odd, and it's 1 over n if n is even. So there you go. A piecewise sequence could work as well. What does this look like if you were to graph it? The table below suggests that d sub n can be made as close as we please to 2 by taking n sufficiently large. So we can get bigger and bigger and bigger. This reminds me of limits, that if I take my n values super, super, super big, no matter what, the value of that sequence, those terms will never be larger than 2. They'll get really close, but they'll never be larger. Now we're going to talk about converge and diverge. And I know that we spoke of these earlier, and I tried to introduce that language. So here's the time when we're going to use it for real. Suppose L is a real number and S sub n is a sequence. The sequence converges to the real number L if for any value, that's a delta, I think that's a lowercase delta greater than 0, there's a positive integer n, so that the sequence minus that limit is less than delta. That's your error. You want to make sure that you're within that error for all integers n all the way up to n. If the series converges to L, then L is called the limit of the sequence, and we write the limit as n approaches infinity, S sub n equals L. If the sequence converges, it is said to be convergent. Otherwise, it is said to diverge. So this entire unit is going to be about converges and diverges. When do we have enough information to prove that it converges? When do we have enough information to prove that it diverges? Figure 3, we have a geometric representation of what's going on with the sequence. The figure illustrates that the beginning terms of the sequence do not affect the convergence or divergence of the sequence. So whatever's happening here in the beginning does not dictate what happens later on. They don't have to. The beginning terms of the sequence can be ignored when determining convergence or divergence. So if we're talking about this stuff in the beginning, that's great. But if we want to talk about terms as they go on, where do you suppose we're headed? Infinity. We're all about infinity. All right, this is going way back. Easy stuff. Show that the limit as n approaches of c is equal to c. Well, if you recall, for limits, there's no place to put this infinity in for n because there's no n in the problem. So I'm not even going to write that. I'm just going to write c, done. For letter B, we would put infinity in place of the n. We know that 1 over infinity is not a real number, but what does it start to approach? It starts to approach 0, so we know that. Properties of convergent series. We can multiply by a constant, you can add, subtract, you have a product. So this is just like limits. You don't have to worry about a product rule, which is really, really nice, just like limits. Quotient, you can just take the derivatives. There's no quotient rule provided you're not divided by 0. The power property is pretty helpful because sometimes you can just deal with the inside without having to worry about that exponent. And the root property just kind of tags along with that. You can take the root or the power all the way to the outside. All right, we are going to show that S of n equals 2 over n plus 3. I feel like I forgot some instructions here. Hang tight. Whoops, definitely forgot the instructions here. Not show that, but we want to find the limit for each one of these as n approaches infinity. So for letter A, we have the limit as n approaches infinity of 2 over n plus 3. So 2 over infinity plus 3, this is essentially 0 plus 3. So we're left with 3. Letter B, the limit as n approaches infinity of 4 over n squared becomes 4 over infinity, which we know is essentially 0. The limit as n approaches infinity, that cube root we can bring all the way to the outside. 16n squared plus 3n over 2n squared. This will become an 8. 16n squared over 2n squared is 8. So now I'm left with the cube root of 8, which is just 2. All right, example 6, show that the sequence converges and find its limit. So we want a limit. The limit, and the limit to where? We're headed to infinity. As n approaches infinity, the natural log of 2 over n plus 3. Well, you can treat this. You can actually bring the natural log to the front. This can be the natural log of the limit as n approaches infinity of 2 over n plus 3. This piece becomes a 0. So now I have natural log of 3. Natural log of 3 is a value. It's a number. It doesn't go to infinity. If it went to infinity, we would say diverges. But we got an actual answer, so we get to say this converges. Okay. The related function of a sequence. A related function of a sequence has the following properties. F is defined on the open interval between 0 and infinity. That is, the domain of F is a set of positive real numbers. That's important. We're only dealing with positives. The right-hand side of the number line. If the function is equal to, well, actually I should say the function is equal to the series for all integers greater than n. So show the related function, for example, 7. Literally all you have to do is write it. You would tell me f of x equals x over e to the x. Replace the n with an x and you're good to go. Theorem, we have a sequence of numbers. F is a related function and L is a real number. So if the limit is L of the function, then the limit of the series is also L. So we want to show that this converges and find the limit. So we're looking at the limit. We're always headed to infinity of 3n squared plus 5n minus 2 over 6n squared minus 6n plus 5. If we put infinity in right now, we have infinity over infinity. How did we handle that in the past? We used L'Hopital. Yay, L'Hopital. So the limit as n approaches infinity becomes 6n plus 5 over 12n minus 6, still infinity over infinity. So L'Hopital again gives me 6 over 12, which will simplify to 1/2. So we have an answer. That means it converges, and the limit is 1/2. Sample 8. All right, we're good with that. Example 9, show that this converges and find the limit. So for example 9, we have the sequence that we want to show that it converges and find its limit. Technically, we don't do math. With the sequence itself, you want that related function. So your related function is f of x equals x over e to the x. Now we would find the limit as we approach infinity of x over e to the x. Right now, this would be infinity over infinity. We know that's indeterminate, so we want to use L'Hopital's rule. So this becomes the limit as n approaches infinity of 1 over e to the x, which is 1 over infinity, which we know is 0. So it converges because we got a value for an answer, and the limit is 0. Squeeze through for sequences. We have a, b, and s are all sequences. Capital N is a positive integer. For every integer, lowercase n is greater than positive. If the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of b sub n, those are both equal to L, then the limit of s sub n must also be equal to L. So in that last example, it said, don't worry about the beginning. Like the early terms don't matter. It's the later terms that do. So in this particular situation, we know that b is on the top, a is on the bottom, and s is in the middle. So if a and b have the same limit, then s, which is sandwiched between, has no choice but to have the same limit. We did this back in Limit World early on. So example 10, show that s sub n equals -1 to the n times 1 over n converges and find its limit. So we want -1 throws a little bit of a wrench into here initially. We have a shortcut for that. We're just not ready to talk about it yet. So I know that the absolute value of -1 to the n, 1 over n, is always going to be less than or equal to 1. If we're dealing with inequalities and absolute value, if we call from algebra 2, we get to write this as a plus or a minus. So -1 over n is less than or equal to -1 to the n, 1 over n, which is less than or equal to the positive version. So what happens is you can take the limit of each one of these or find the limit of each one. So the limit as n approaches infinity at -1 over n is equal to -1 over infinity, which would be 0. And the limit as n approaches infinity of 1 over n, the positive version, is 1 over infinity, which is also 0. So because no matter which version we have, the positive or negative, because they both go to 0, we know that it converges, and we found the limit. That limit is also equal to 0. Divergence of a sequence to infinity. The sequence diverges to infinity, we have infinity for answer. So if in any positive number m, there's a positive integer n, so that whenever n is greater than n, s sub n is greater than n. I know that's a lot. Basically, show that it diverges. We want the limit as n approaches infinity of 1 plus -1 to the n. So if you recall limits, you can pull this apart. You can have two separate limit problems, which is what I want to do here. The first piece is easy. The limit as n approaches infinity is 1. There's no place to put in that infinity, so I know that this becomes 1. For the second piece, well, they did it together in the textbook. The second piece, say we start with 1, that's going to be a -1. And then it's a positive 1, and then it's a -1, and then it's a positive 1. It alternates back and forth. So because it doesn't approach any one limit, the side has no limit. So because it doesn't converge to any one thing, we say that it diverges. And then letter B is so easy, it seems tricky. So this is the limit as n approaches infinity of n, put infinity in place of the n. This is very much infinity, so we can say that this diverges. No problem on this. All right, so now we are looking at convergence and divergence of a geometric series. This is our sequence, I keep saying series. Geometric series. This is a very specific situation. A geometric sequence is where we have r, which is a real number, raised to an exponent. If that r is between -1 and +1, it will converge to 0. If r is equal to 1, then it converges to 1. Otherwise, it diverges for all other numbers. I've also seen this expression written as the absolute value of r is less than 1. Those two mean the same thing. So determine whether the following geometric series converge or diverge. You want to take that r is equal to 3/4. R is less than 1. So I know it converges to 0. That's it. That's literally it. The next one, r is equal to 4/3. R is greater than 1, so it diverges. And that's all you have to know about that geometric sequence. Example 13, determine whether a sequence is bounded from above or bounded from below. Show that it converges and find the limit. So again, we're talking about infinity. The limit is n approaches infinity of 3n over n plus 2. If we put infinity in right now, that's infinity over infinity, that's indeterminate. So we can use L'Hopital, and I get 3 over 1, which is equal to 3. So what does that mean for the bounding for us? So as we go to infinity, this goes as high as 3. Now your textbook does it a little bit differently. And because we're talking about sequences, we start at the value of 1. So I'm also going to look at this as the limit as n approaches 1, only from the right, not the left-hand side, of 3n over n plus 2. If I put 1 in for both of those n's, I wind up with 3 over 3, which is equal to 1. So it's bounded from above by 3 and by below, I should say from below by 1. So no matter what, all those terms are sandwiched between 1 and 3. Let's try the same thing for the next one. The limit as n approaches infinity of 4n over 3. Well, this would be equal to infinity, so it's not bounded above, because it goes up and up to infinity. Let's talk about the limit as n approaches 1 from the right of 4n over 3. I guess this should technically be x's, but that's okay. It would be 4/3. So bounded below by 4/3. This one alternates. This one's probably the easiest to see. But n is the term, so if I put in the 1, I start at -1. Then this would be +2, -3, +4, -5. This one is not bounded. Because as you go on, the ends get larger and smaller. I know you're not going to be happy with that, and you're going to have questions for me, and I will answer them. But try not to overthink these too much. That one keeps going up and keeps going down. All right, here we go. Increasing, non-decreasing, decreasing, and non-increasing. Your only two options don't have to be increase or decrease. They could actually hold steady, be horizontal. So you can say that it's not increasing or not decreasing. So you just want to make sure that you are comfortable with those words. A couple specific types of sequences that we have is an algebraic difference. Those will always have a pattern where you can show increasing or decreasing. An algebraic ratio I have for you, and derivative. So let's talk about example 14. I think this is last page. Determine whether a sequence is bounded from above or bounded from below. Show that it converges and find its limit. So for letter A, if I go bounded below, what happens if I put a 1 in there? I get 1/2. And above would be going to infinity. So infinity over infinity, orbitalis would be 1. So this is bounded below by 1/2 and above by 1/2. Sorry. So I've mistaken my directions here. So I apologize, I have a mistake in directions. This should be show increasing or decreasing. All right, new plan, example 14. I don't love it. It's not essential to what we're doing. We're gonna skip over this. We'll have these tests later on, but right now I just think it's too much for what we're doing. All right, so skip example 14 for me. And then last but not least, a theorem is increasing or non-decreasing sequence that is bounded from above converges. A decreasing sequence is bounded from below will converge. Example 15, determine whether the sequence converges or diverges. So 2 to the n over n factorial. I don't want to do this one either. We will. It will be something that we do called the ratio test. I'm just not ready to talk about it yet. So lucky you. Skip 14 and 15.